when external moment increases due to heavy loadings in span support relationships. There is a need of providing extra flexural strength in terms of extra moment of resistance to a beam section. The beam which is provided with extra steel in compression zone to impart this extra flexural strength is known as doubly reinforced beam. Two plans are available for this requirement. 1. Increase dimensions of section. Increase in depth is more beneficial. 2. Provide extra reinforcement in tension zone, thus section becomes over-reinforced. But due to some practical limitations we cannot provide extra depth and extra steel in flexure section. To cope up above need, one more suitable situation is there to provide reinforcement in compression zone. The sections which contain reinforcements in both tension and compression zones are called doubly reinforced beam sections. To draw and learn stress-strain curves for concrete and steel. Step by step, see coming all segments. First, have a quick look on beam section. The beam section has following physical parameters. B equals width of the section. B equals effective depth of the section. D dash equals depth of center of compression reinforcement from top fiber equals 50 millimeters. B equals total depth of the section. AST equals area of steel under tension. ASC equals area of steel in compression. CC equals the clear cover to tension reinforcement. CC equals 25 mm. CC dash equals the clear cover to compressive reinforcement. CC dash equals 25 mm. The stress-strain curve of concrete is obtained from experiments over many cubes. It has following salient points. 1. When load is increased on the specimen, the stress-strain curve is parabolic up to strain of 0.002. After that it becomes straight line to reach ultimate strain before failure equals to 0.0035. 2. The ultimate stress taken by concrete cube ranges 0 to maximum value of FCK. The factor of safety taken for concrete is 1.5 to accommodate variations on site and other quality reasons. For design purpose, the compressive strength of concrete in the structure be assumed to be 0.67 times characteristic strength. The partial safety factor gamma MC equals 1.5 shall be applied in addition to this. So final stress taken by concrete in compression is taken as 0.446 FCK. Figures 1.2 and 1.3 show the representative stress-strain curves for steel having definite yield point and not having definite yield point, respectively. The characteristic yield strength Fy of steel is assumed as the minimum yield stress or 0.2% of proof stress for steel having no definite yield point. The modulus of elasticity of steel is taken to be 200,000 N per square millimeter. For mild steel, the stress is proportional to the strain up to the yield point. Thereafter post-yield strain increases faster while the stress is assumed to remain at constant value of Fy. For cold work bars figure 1.3, the stress is proportional to the strain up to a stress of 0.8 Fy. The two grades of cold work bars used as steel reinforcement are Fa 415 and Fa 500 with the values of Fy as 415 Newton per square millimeter and 500 Newton per square millimeter respectively. The tensile strength of the concrete is ignored. The stresses in the reinforcement are derived from representative stress-strain curve for the type of steel used. Typical curves are given in Figure 1.3. For design purposes, the partial safety factor is equal to 1.15 shall be applied. The maximum strain in the tension reinforcement in the section at failure shall not be less than 0.87 Fy upon As plus 0.002.
For complete course and step-by-step illustration, please subscribe full course on Structural Analysis and Design app. Also subscribe YouTube channel Matrix Digital Solutions. Thanks for watching.